Chemical kinetics. Chemical kinetics is an important topic in chemistry because oftentimes the chemist wants to know how quickly a reaction is going to proceed. And knowing the rate of reaction is an important thing. The reaction rate is a change in concentration of a reactant or product per unit time. So initially, if we have all reactants and no products, we tend to move more quickly than once products have begun to be formed. Don't forget that collision theory says for reactants to form products, collisions must occur. So the greater the concentration of reactants, the faster that products can be made. If you wanted to look at it mathematically, you could look at this formula. Rate essentially is change in concentration over change in time. Concentration of A means concentration of A in moles per liter, in other words, molarity. A is the reactant or product being considered. Sometimes we talk about rate of products being formed or rate of reactants being lost. Here's an example of a chart showing the concentrations of reactants and products as a function of time for a particular reaction. You noticed in the beginning we have all reactants and no products. And as time marches forward, we start to gain products and lose reactants. If you wanted to look at it in a graphic manner, here it is, concentration versus time. You can notice that the green line shows the reactant, and over time the reactant is decreasing. And you can notice that the other two lines, the blue and the pink, are increasing. Those are products. You can see too that if you wanted to know a certain point on the curve, you can find the slope of the tangent line. You might also think, gosh, I might as well use calculus to do this, but remember, this course is not a calculus-based course, so we will have to remember how to find slope of the tangent line. Or instantaneous rate. Instantaneous rate is the value of the rate at a particular time, and that's what we saw in the previous slide, the triangle, because we want to obtain that by computing the slope of the line tangent to the curve at that particular point. But what we focused on in intro, and we're going to remember again, is something we call rate law. Rate law shows how the rate depends on the concentrations of reactants. So, for example, for the decomposition of nitrogen dioxide, here's an example of what a rate law would look like. Remember, rate equals K times the concentration of NO2 to the N. The N is the order of the reaction. Is it zero order, first order, second order, half order? And K is a rate constant. The concentrations of the products do not appear in the rate law because the reaction rate is being studied under conditions where the reverse reaction does not contribute to the rate. So, if there's only one reactant, that's the only thing that participates in the rate law. If there are three reactants, then there are potentially three things that can contribute to the rate law. The value of the exponent n must be determined experimentally. You can't assume that the coefficients that you see in a balanced equation are the exponents, like they were back when we talked about Q, for example, products over reactants. There, the coefficient was the exponent. That is not the case with rate law. There are different types of rate laws. Differential rate law, which is the one we learned in intro and we're going to remember again. It's going to show us how the rate of reaction depends on concentrations. And the integrated rate law, it shows how the concentrations of species in the reaction depend on time. The integrated rate law will be something that we will discuss in another video. Remember, we typically consider reactions only under conditions where the reverse reaction is unimportant. Our rate laws will only involve reactants. And because the differential and integrated rate laws for a given reaction are related in a well-defined way, the experimental determination of either rate law is sufficient. experimental convenience usually dictates which type of rate law is determined experimentally. Knowing the rate law for a reaction is important, mainly because we can usually infer the individual steps involved in the reaction from the specific form of the rate law. Remember, there is a certain series of steps that a reaction has to go through to form products. We call that a mechanism. So if we know something about the rate law, then we can infer something about the mechanism of that particular reaction. Remember again, we can only use experiments and data from experiments to figure out the exponents for the rate law, the power to which each reactant concentration must be raised. The method of initial rates is what we learned in intro, and we're going to reuse again to figure out the value of the exponents. The value of the initial rate is determined for each experiment at the same value of t as close to t equals 0 as possible. Now your book will show you a variety of different ways to solve these method of initial rate problems. I'll show you what we learned in intro and then add on to that. Several experiments are carried out using different initial concentrations of each reactant, and an initial rate is determined for each run. The results are then compared to see how the initial rate depends on the initial concentrations of each of the reactants. So the sum of the exponents in the reaction rate equation is the order of the reaction. So for example, here's a generic reaction with A and B. Rate equals K, A to the N, B to the M. The order of this reaction is whatever the number for A is, the exponent for A, or N, added to whatever the exponent is for M. So let's say A is first order and B is first order. Then the overall reaction order is 2. And of course K is the rate constant. How do exponents, orders, in rate laws compare to coefficients in balanced equations? Why? Well, again, they have no relationship to the order of the reaction. These things have to be determined experimentally. Here's an example of figuring out the rate law. In the beginning, you can see I've written the actual reaction between bromate ions and bromide ions in an acidic solution. If we want to figure out the rate law, you can see rate equals K times BrO3 negative to the X, Br negative to the Y, and H plus to the Z. The X, Y, and Z are just placeholders for numbers that are going to be the order of that particular reaction or reactant in that reaction. The method of initial rates, you might remember, involves comparing different experiments to see how manipulating the concentration changes the rate. So here's an example with 4 experiments. You notice experiment number 1 has a certain concentration of BrO3, Br negative, and of hydrogen. And then that's the rate. 4 experiments are shown here, and it's our job to analyze the experiments and figure out what the exponents are. So in intro, this is how we did it. We're going to look at 2 experiments, and I think the first one we're going to look at is experiment 1 and 2, because you'll notice how hydrogen stays the same, bromide ion stays the same, but the bromate ion is doubled. So you can say, all right, I know that. If I isolate experiment 1 and 2, and I can see what BrO3 negative is, how that's changing, and I can see how the rate's changing, that might give me a clue to what order the reaction is in terms of BrO3 negative ion. So I doubled BrO3 from 1 to 2, and the rate also doubled. That means it's a 1-to-1 relationship. So therefore, the exponent there is a 1, or as you will see, 2 to the first power. I'll show you that in a minute. I'm going to do the same with the next 2. I want to try to find one that isolates Br negative and one that isolates hydrogen ion. So let's look around. It looks like 2 and 3 isolates Br negative ion, because this stayed the same. It doesn't matter that it wasn't 0.1 to 0.1 like it was from 1 to 2. This stayed the same, and this stayed the same, but this changed by going up by a factor of 2. What happens to the rate? Well, it too went up by 2. If you can't see that, of course, you can divide it out and look at the calculator, and it will tell you it's a 2. So again, Br negative is first order. And then finally, we need something that isolates hydrogen ion. We're obviously going to use experiment 4 because we haven't used it yet, and some other experiment. Looking quickly, it looks like it is this one. This is times 2. Now, not everything is times 2, but here in this example it is. Notice bromide ion stays the same, bromate ion stays the same. What happens from 1 to 4 goes from 8 times 10 to the negative 4 to 3.2 times 10 to the negative 3. That's times 4. That means it is second order because it went from 2 to 4. Or if you want to think about it like this, 2 squared. Notice the overall order of the reaction is fourth order, 1 plus 1 plus 2. And it's first order in bromate, first order in bromide, and second order in hydrogen ion. Now that's pretty easy when you have some nice looking data like this. But what do you do if you have a lab where your data isn't as perfect? At least the rate doesn't look as perfect as these perfect multiples. Well, you might have to actually write out the rate. So you notice the rate here. If I wanted to compare two rates, let me just show you experiment 1 as compared to experiment 2. Now I think by looking at it the way we did in intro, at least when it's pretty easy, it's easy to see its first order. How would we do it mathematically? You know, what if it wasn't a whole number? What if it was 1/2 order or something else tricky? How would we figure it out otherwise? Well, you know we can figure out rate by this formula with the x, y, and z up there. So the rate of experiment number 2, I'm going to do 2 as compared to 1. You notice the rate of this one is 1.6 times 10 to the negative 3. And the rate of the other one is 8 times 10 to the negative 4. And what I'm doing is I'm simply plugging in the information from the experiment into the rate law and leaving the exponents, x, y, and z. Don't forget k, because that's a rate law constant. Now, the first one, experiment number 2, I'm doing that one first because when I divide here, I like to have a whole number. If I divided the other way, I'd have 1/2. It would still work, but I just prefer whole numbers. So I'm putting experiment number 2 on the top and experiment number 1 on the bottom. I'll just write that there so I can remember. All right, so I put 0.2 to the x, 0.1 to the y, and 0.1 to the z. I've made my line entirely too long. That's fine. Experiment number 1, 0.1 to the x, 0.1 to the y, and 0.1 to the z. All right, now I can start reducing. You notice this is the same as this, and this is the same as this, and k is the same. I like this kind of reducing. 1.6 times 10 to the negative 3 divided by 8 times 10 to the negative 4 is a 2. Remember, I like the whole number. 0.2 divided by 0.1 is 2, and of course, to the x power. Now, it's pretty easy to solve for x. And I think I mentioned earlier, it's like 2 to the first. And of course, that would have to be a 1 there to make it work out mathematically. That's why it's first order in terms of BrO3 negative. You could do the same for the other reactions, and you would get a 1 for Br negative and a 2 for hydrogen ion. So if you happen to get a series of numbers that don't all cancel out nicely, and that's easy to figure out what order the reaction is, one other method would be to simply write the entire rate law out, plugging in the numbers carefully, reducing, and then solving for your exponent. Another factor that you might have to do, another question you might have to do, would be to solve for the value of k. That's a very common question. Pretty easy to do. You pick any experiment once you have your exponents, in this case 1, 1, 2, You pick any experiment, could be experiment number 1 or 2, 3, or 4, and you plug in the information. You plug in the rate. So if we're using experiment number 1, we'd use 8 times 10 to the negative 4. And we figure out, we don't know what K is, but we know the BrO3 is 0.1 to the first. Br is 0.1 to the first, and hydrogen is 0.1 to the second. We would solve algebraically and solve for K. If we had plenty of time and we wanted to verify that that was the right rate law, what we would do is we would go through with experiment number 2, plug in that number. We should get exactly the same value of K. Why? Because it's a constant.